Hello, Math 1324 students. I am putting together this video pretty rapidly because I've had some questions from students about the introduction to annuities in section 5.3. So let's get started. So what are annuities? Annuities are like the only way to grow money faster than mere compound interest. Annuities are like having compound interest a compound interest account, but instead of just putting a lump sum in the beginning and walking away and coming back after 20 years and seeing what's there, you keep pumping more money into the account, and each payment that's put in is accruing as much interest as it can over the course of the annuity, right? So for example, let's say you have some annuity account that's 30 years old, right? But each time you're making the same payment, it's a fixed payment made over all those years. And in fact, the payment is made N times per year. So using the same notation that you've been using in compound interest. This is what most textbooks use, not the book's notation, which is trying to save you steps but doesn't connect anything to what you knew before. So if N is the compounding rate, the number of times your account is compounded, meaning compounding means the balance is multiplied by a number greater than 1, so the balance is increasing. Compounding is a good thing. R, as always, is the APR, the annual percentage rate, and T, as always, is the number of years. So if that's the case, look what happens. So let's say you've had that in there for 30 years and making 12 payments a year. Annuities often are tied to a monthly income, and a payment is made every month, often. Not always the case, but often. So let's say for 30 years, 12 times a year, you've been making these payments, the same fixed payment. Well, the oldest payment has been in there quite a long time. So just like compound interest works, you would multiply the payment times 1 plus R over N, raised to the total number of payments of months that it's been in there. Well, how do you compute that? That's 12N times T, the 30 years. Now, why do we have minus 1? Well, the oldest payment in there didn't earn its interest until a month, let's say, had gone by, right? So it's NT minus 1. This next oldest payment gets multiplied by 1 plus R over N raised to the NT, but minus 2 months, and so on down to your next to last payment and its interest. The payment multiplied by 1 gives you the payment amount that you've pumped in there. The payment times R over N was the interest that the next to the last payment earned. And then your last payment hasn't earned any interest. So it's just payment times 1, right? Okay, so add all that up together and you have the amount in the annuity. Now, from algebra, but look, we have this expression raised to some big quantity minus 1, some big quantity minus 2, all the way down to just raised to the first power plus 1. We have a trick from algebra. We know, let's see now if I can get your screen back on here. From algebra, yes. We know that if you have a quantity x raised to capital M, I'm just using that as a variable, minus 1, that can be factored. Remember, x cubed minus 1 is factored into x minus 1 times x squared plus x plus 1. Well, this can be generalized. So why do we care? Well, see that? You've taken the same basic quantity. Oops. See that over there? You've taken that same basic quantity and raised it to the m minus 1 power. And you're adding it to itself raised to the m minus 2 power plus ... itself raised to the first power plus itself raised to the 0th power, if you like. That polynomial right there, well, if you multiply it by x minus 1, it would equal to this. So therefore, that polynomial, if you take that x minus 1 and divide it by x minus 1, you get that polynomial. So we use that trick over here. We say, therefore, the future value of your annuity, which is a fancy way of saying the amount in the account after T years, compounding n times year, making a payment also every n times per year for T years, will therefore be equal to the payment times, this is our replacement for x, 1 plus r over n, raised to the nt minus, oops, sorry, there might be a, yeah, that's right, raised to the nt, because just like that, here was x to the m minus 1, but when we make this quotient, that becomes x to the m minus 1 over x minus 1. Right, okay, so here we have, here's our, this base here is our x, that is our capital M minus 1 divided by, now if we really had in here in the denominator, we had 1 plus r over n minus 1. But everybody knows that just reduces to r over n. Now your book tries to introduce notation and call that I, and then but they have a problem with not sticking with the notation that everybody's been using forever. N is the compounding rate, number of times you compound the money per year, and T is the number of years. So this should be NT right here. Okay, so this is your formula for calculating the future value of an annuity. This is the formula that's always been. Your book is trying to make things more complicated by introducing some notation that in a few sections they're going to abandon anyway. So let's just get right to the point and use this formula. So for example, let's say, suppose you have an IRA, individual retirement account annuity, simple annuity, regular annuity, and you've been making payments of $1,750 every month, you know, from your salary, which might be $10,000 a month, something like that. And you've been doing that for 25 years. You were promised that the APR on that annuity would be a 4.8%. So how much is in that annuity? Which, when it's a retirement account, often gets called a nest egg. All right, so you've been saving up all this money, you're about to retire. This amount in the account is going to be used to feather your nest for your retirement. That's why it gets called nest egg. So how much is in there after 25 years? Okay, so using this formula, we plug in, the payment is $1,750, the interest rate was 0.048, number of times we're compounding a year because it was monthly payments is 12, raised to the NT, 12 times 25 is the total number of payments you make over that whole annuity, minus 1, that's from here, and it's divided by 0.048 divided by 12. Your interest rate, your annual interest rate divided by number of months gives you essentially what is a monthly interest rate. So there it is. Now, how are you going to enter that in here? That's what students seem to have trouble with. Couple of things. Because of the graphing calculator, you can do this almost in one step. Problem is, then you would have to deal with nested parentheses, raised to parentheses, and then there's, you know, this long division symbol actually means group that numerator together and divide it by that denominator. So there's parentheses upon, you know, nested parentheses here. If you try to do it in a oneer, students usually don't do it well. So what I suggest is treating this formula, like some others we're going to come across, as a kind of onion, many, many layers, and you can most quickly and most accurately, without writing anything down and possibly making some transcription errors, do it the following way. Go to the innermost part. The innermost part would be that we need to compute this before we raise it to that power. So that's what I'm going to start with. So I'm going to enter here 1 plus 0.048 divided by 12. And then what I do is I press enter just to compute that little bit. So that means currently in my calculator is this quantity. And using a different color pen to keep things straight, and in case I get interrupted, I can pick up where I was. So this amount right here is in here to all accuracy, the most accuracy of the calculator. What's supposed to happen to this quantity? Well, this quantity in red is supposed to be raised to that power. So now I just say raised to the, and so it takes the previous answer and raise it to the, use parentheses, 12 times 25. Let that calculator do that calculation, and you press enter and you get a quantity. What is that quantity? Well, that's after I've taken this red box base and raised it to that power. So I just use another pen to denote that. And so what I'm looking at right here is exactly that quantity. I don't write this down. I just keep it there in the calculator. I keep going, working back outwards using PEMDAS, order of operations. What's supposed to happen next? Well, I'm within these brackets and I'm in that numerator. So this quantity, I need to subtract 1. So I subtract 1 and I press enter. Now I've got some 2.3121 blah, blah, blah. I don't even really look at it so much. I just say, right, what's in the calculator is now this numerator. What has to happen next? I have to divide by this number, and then I got to take the result and multiply by this. I could go in either direction because multiplication, division are commutative. Did I say that right? Maybe I should say associative. So this quantity that I have in here is that big fat numerator. So what I'm going to do is divide by this first because I've got these brackets I'm kind of working my way out of. So I'm going to divide this quantity that's in here. That's what's in the red box, the numerator. I'm going to divide it by the quantity 0.048 divided by 12. Press enter, and now some quantity is in here. What is it? It's this whole quotient, the result of this division, and therefore everything inside those brackets. What's left? I need to multiply it by 1750. So I take that quantity and I multiply it by 1750, and now I have the future value of this account in all its glory. So what is that? Well, as I've been encouraging you in other videos, what I tell my students to do is at first write down what you're seeing coming out of the calculator. Admit that's what's going on. Just write down the digits. 1011.578.457. Okay, get that down in case you happen to hit another keystroke and mess things up. Now you have the calculator's output. Secondarily, you need to round to the nearest penny, and you need to put on commas and dollar signs, right? So what is this quantity? Let's see. To the nearest penny, that would be 46 cents. So I have $578.46 in there, 11,000 and 1 million. So if for 25 years, 12 times a year, you deposited $17.50 into the annuity, if that's all you did, if you, not into an annuity, but let's just say under your mattress somewhere, without growing the interest. In other words, how much of this money is actually yours that you put in, right? So on the side, you can calculate that and say, right. So if I take $17.50, multiply it by 12, for every month you're doing this, times 25, that would equal, and I just stuck it in the mattress, right? I'm not gathering any interest. 1750 times 12 times 25. I put into this $525,000. The person holding this IRA, right? They put in $525,000. That's all they put in. Because that interest rate was a 4.8%, it, instead of just being $525,000 or $500,000, it's over $1 million, right? And so how much was the interest? Well, this amount is how much you put in, the 525,000. And so to quickly calculate it, just subtract the amount that's in the account, 1011,578.46. You'll get a negative quantity, but you can just leave off that negative sign and say, wow, the interest. So what was this quantity equal to? It was the amount that we put in, the 525,000 plus interest, and the interest that we earned by not putting it in the mattress, but by putting it in the annuity, was this difference, $486,578.46. So there's no other way to calculate the interest earned, or is as easy as just doing this. Using the future value account, formula, the amount in the account after T years, and then calculating on the side how much of that payment money was coming from your wallet, from your salary, versus because of that APR guaranteed to you as a benefit of your employment. Instead of just $500,000, you look at your nest egg and you see over $1 million. Okay, so the interest earned you almost as much as you put in. The interest essentially doubled your money, right? Okay, hopefully that will help.